Now I hit record. Now
Oh,
it's
sorry.
official. Yeah, I have to like launch into it with my YouTube voice. Hey guys, welcome back to my channel. We're here today to talk about multivariate models. Yeah, no, I can't do that. It's
Well,
gonna
see,
hurt.
I talk through my setup when I start class too. It's like, you usually talk through, and you didn't mention
Yeah.
that you did this.
Yeah,
So I'm
I
like,
gotta have the official beginning of the recording, otherwise it doesn't count, even though half the time I'm like mid-sentence when I hit record anyway, because, you know, it's one contiguous thing. So I was just saying we're gonna go over more of example 5, finish up lecture 5, and start lecture 6 today. And I would normally say, does anyone have any questions on homework? But you don't, because you turned it in. So hooray, now it's on my to-do list instead of yours. My intent is to get you feedback within the next week, and revisions are optional. If you get your score and you're like, it's fine, I can live with this, you don't have to touch it. If you want to be a perfectionist and get your half a point back or whatever you missed for things, then you're welcome to do that. I just ask if you're planning to revise to make sure you leave in my comments and use track changes so I can see what I asked you to fix. That will make both of our lives a little bit easier. I will let you know when that is available. As I was just saying before, I captured it on recording. Your last 2 things to do, homework 5 is going to be available probably starting tomorrow. That's going to be a path model. And you are able to use R, Stata, or M+ as a new software package on that. M+ is going to be used in the structural equation modeling course, as well as I use it in the advanced longitudinal course. So it's something that would be good to pick up if you haven't. However, if learning a new software package is not part of your mission right now, you're just getting through, I see that, I hear you. So you can use R or Stata as well.
does that include, when you say multi-level, are you including clustering with that thought or
Um,
not?
in the clustered class, I think I spent the last like 2 weeks using an example that involved M+, but not any homeworks. It was more like an advanced topics sort of deal.
Fair enough.
So yeah, nothing in that, but it does, if you want to do anything multivariate on clustered data, you will end up using M+ for that, is what's gonna happen.
Sounds good. Thank you.
Yep. Okay. The other thing then is your last bridge activity, which is going to be a blend of a formative assessment and a bridge is what I decided on.
Ooh.
So I've got one story problem that's an essay question. I will give you the points if you give me an answer. Okay, I'm not grading it for real. Just try your best, and we'll talk about what I had envisioned for that. It's based on a true story, actually.
Very good.
The other part of it is multiple choice questions about some of the aspects of path modeling that I want you to learn from in terms of vocabulary, degrees of freedom, and just those sorts of concepts. So those should be more straightforward answers that do have a correct version, which we will go over per usual. Okay. Anything I'm forgetting or questions?
Exciting.
All right, then let me see here. Let me go over to lecture 5. So I know since I've hit parts of this and not other parts, what I wanted to do just briefly is give you what I view as a high-level summary, pieces of things I want you to get out of this, not the nitty-gritty. What I intend to do is track down the videos from last year where I did a more detailed explanation of the slides we haven't covered. That way you have that for future reference. I'll see if I can find that. But in the interest of time, and I think path modeling is more important, I just want to hit the highlights. So think of it as like you binge watched a TV show that ended at season 2, and then like 18 months go by, and then season 3 comes out. And you're like, I don't remember anything about this show, but I know I watched it. And usually the people who make the show know this is going to happen. And then they're like, last time on Severance, or last time on Shrinking, or like they give you that like 1-minute recap. That's what my goal is here. So 1-minute recap of 39 slides. Go. Maybe more than a minute, but not 39 minutes. Let's put it that way. So the idea of multivariate is anytime you are predicting multiple outcomes at the same time from the same sampling unit. And I'm saying that generically because a sampling unit could be a state, a company, a person, a classroom, a unit broadly construed. So in example 5, our unit is a family, and the multiple outcomes are different people from the family. You would want to have multivariate models in many different cases. In particular, when you're interested in looking at mean differences across your outcomes would be one. When you're interested in comparing effect sizes for the effects of your predictors across outcomes, so is it more related to outcome A than outcome B, that kind of thing. Dyadic data would be another special case, so actor-partner models I've mentioned a couple of times. If you're interested in, say, a mother-child dyad and you want to know how mom's behavior affects the kid's response and how the kid's behavior affects the mom's response, you got to have all those variables as part of the story. The most natural way, I think, to operationalize those models is path analysis. That's what we're heading to. In terms of how the models need to differ based on the fact that they're multivariate, the big idea is that you have to build in a way to tell the software that the outcomes from the same sampling unit get to be correlated. That's the big idea, because they're going to be. And if we pretend otherwise, all of our effects are going to be some kind of wrong. The standard errors need to account for the fact that we have somewhat redundant information. Outcomes from the same person or whatever tend to be related. If we are in normal land, so like general linear model land, and you just have a couple more outcomes rather than one, that's super easy. We just say, hey, let the residuals from the same unit either have the same variance across outcomes or different, or, in addition, the covariances among the same, from the same person, they get to have a covariance that's the same across outcomes or different. So it's just a question of looking through a couple possible choices and deciding which one fits relatively best, as indicated by likelihood ratio tests, AIC and BIC. Unstructured is the one that I would tend to recommend unless you have a lot of outcomes. That's the one that can't be wrong. It's the most complex version. All the variances get to differ, all the covariances get to differ. That's what we're doing in example 5. Where the problem comes in, though, is you can only do that in normal land. If I have a binary outcome, what's my residual variance going to be? I don't have one. If I have a count outcome, what's my residual variance going to be? I don't have one. If I have a skewed continuous outcome, what's my residual variance going to be? Hey, you're seeing the pattern here. And guess what? If you don't have an estimated residual variance, you don't have estimated residual covariances. It's not possible. But you still have to build in a correlation somehow. So there's a backdoor way to do that, which I have some very hand-wavy slides in, I'm going to be quite honest with you in here, introducing the idea of something called a random intercept. If you plan to take coursework in multi-level or mixed effects models, you will see this again. If you take design of experiments, I believe this shows up in there as random effects as well. But the key idea is, let's say that we have 5 outcomes from the same person. This is slide 22 within lecture 5. And let's say that they're longitudinal. So 5 occasions of the same measure. The idea of a random intercept is functionally building in a deviation between what is predicted for the sample on average and what is predicted on average for you across your outcomes. So we're splitting what we used to call error into 2 components. One, because of you, like this purple person is below the mean all the time, so we just give them like a constant shift. And then E is what's left relative to what's expected based on the person. So we are introducing what is conceptually equivalent to a person main effect in the model to control for which person the observations came from. But we're doing it as a random effect, meaning we're not like getting separate slopes for person 100 and 101, 102. We're getting a variance across people. And that then in turn allows us to say, hey, why is it that some people have positive U values, meaning they're above the mean, and some have negative? Well, it's because of person characteristics. So you can explain why some people have higher means than others, and then you can explain the remaining deviations that are occasion specific. And it works out that if you have normal types of data, you can do this instead of correlations, and that's what is required when you have unbalanced data, so different sets of outcomes across the same sampling unit. In generalized versions, this is pretty much all you can do. So you will see this implemented in example 6b, where I have a path model that ends in 2 binary outcomes. I need to find a way to make them related somehow without directly allowing their residuals to correlate, because I can't do that. So I'll show you a trick that introduces something, a latent variable that essentially captures these random intercepts. So this is a placeholder for if you want to do multivariate analysis for generalized outcomes, you're going to have to learn about random effects. But that's not this class. This class is just setting the stage for why that is necessary. Okay, questions so far? Okay, in terms of setting up models, we talked about different ways of setting up the fixed effects. General intercept, where the slopes that distinguish which outcome is which tell you about mean differences. This is useful if your multivariate outcomes are like flavors of one idea. So for instance, measuring achievement per occasion Like if you're thinking of it as one variable that has 5, and you want to know if achievement changes over time, this version of the model would allow you to look at that. Instead, though, if you're thinking of 3 different outcomes or 4 different outcomes and you're not trying to compare across them, then this isn't going to help you. This is just going to be confusing. So an alternative version of the model, what I call an outcome-specific parameterization, then allows you to use dummy codes, essentially. So DVC, for instance, is a 1 if I'm predicting that row of data and a 0 otherwise. And these turn on and off each of the fixed effects. So it's as if you're estimating a linear model for each outcome separately but simultaneously. And that then allows you to do whatever comparisons across outcomes would be of interest. It allows you to look at dyadic relationships and mediation relationships is where we're going to end up with the path analysis stuff. So this is what path modeling uses, is essentially this idea. But we don't have to have the switches if we're using software that understands that we want to predict multiple columns simultaneously. This trick is necessary when you're using software that only is built for one column, and you have to shove all of your outcomes into it in order to make that work. So we're headed into a fully multivariate space. Okay, there. I think I did it. Those are the main points that I want you to have. So we need multivariate models whenever multiple outcomes from the same thing. Different ways of setting it up can be more or less useful. If you have generalized models, you'll need something called random effects to build in correlation patterns across your outcomes. There. Those are my take-home summaries. And it probably says that on the slide, but I'll just say it out loud in case. Converging evidence. All right. There. So example 5. So the goal of this example is to show you what this would look like in standard one-column univariate software, and then show you how that translates into a path model framework. So we're going to re-estimate the same model we end up with in path models to finish out this handout. So the story for this, just to remind you briefly, these are real data. These are a bunch of families collected that were targeting an adult child, and they recruited the child's parents, mother and father, and then adult child of either gender. So these are older data of complete families. The outcome we're interested in is attitudes towards marital gender roles, where higher scores mean a more traditionally conservative attitude. The other predictor we're using is each person's level of education, and then the gender of the adult child. So the first thing we had to do is to reshape the data into a format where each row is for one family, into a long or stacked format where it's one row per outcome per family. So that's what we would normally have, it's just that now we have this distinction as to which outcome and which sampling unit we're talking about. So I have an example of how to do that using reshape in Stata, as well as reshape in R. The code in SAS is actually more cumbersome than this, but I do have an example of that in the online files for any SAS users. Then we started looking at models. Let's see, how much of this do we need to go back over? Is this looking familiar at all or unfamiliar? Review or re-go over, I think is the question.
At least review.
At least review?
Yeah. Could I ask, could we briefly go over again the difference between when we want to do the general intercept parameterization and the occasion-specific parameterization? Because I think that's also something that I haven't gotten very thoroughly yet. And then, like, which one are we looking at right now?
Okay. I'll answer the last question first, actually. The one we're going to look at is both. So I have like model 0A and then model 0B, so mapping them onto each other. The more important question is, when would you want to do both? Or which one lends itself? I would say that if you have conceptualized your repeated measures in a traditional repeated measures kind of way, so you have what you're thinking of as one conceptual outcome, but you have like 3 or 4 flavors of it. So in a traditional experimental task, for instance, let's put it in the context of cognitive psychology, you might have someone do a task without any distraction, and then maybe a task with auditory distraction and something with visual distraction, something like that. So the outcome you'd be interested in is some measure of task performance under each 3 conditions. But the reason you would go to the trouble to manipulate and to give each subject the same 3 flavors of the task is to see how they compare. How much worse does their performance get when they're distracted relative to their baseline? So dual attention studies, for instance, use this type of format. If that's how you're thinking about it, like you have one thing and you want to know differences across the flavors of the one thing, that's a general intercept plus slopes to differentiate which outcome is which version. That aligns itself very nicely with traditional repeated measures ANOVA. The only difference in what I'm showing you is that we're using likelihood estimation instead, so that you don't have to get rid of somebody who doesn't have all the possible outcomes. Otherwise, you do. So if you have, like, say, a pre-test, post-test follow-up design where you're collecting one thing over time and not everybody comes back, using mixed in Stata or using LME 4 in R will allow you to keep whichever occasions you do have, whereas going with straight ordinary least squares, traditional repeated measures analysis of variance, kicks them all out. So it's better to keep more data if you can. The other version of it, the outcome-specific intercepts, is analogous to what happens in path models, and that is more useful, I think, if you're thinking of your outcomes as not flavors of one thing, but different things entirely. So you might have standardized test scores in math, ELA, and science, and you're interested in whether some effective teacher training improves language scores more than math scores. Like, you're not saying they have higher language than they have than math. Like, you're not comparing the means across subjects, but you're interested in how does my predictor affect this outcome? How does it affect this one and this one? And you might want to say, does it affect it more? But that's a different question than whether the outcomes have different mean levels. Okay, does that help? Yes, okay. Happy to answer more specific case examples as well. But this one, I think you could make an argument either way. In this example, I can think of it as marital attitudes is the thing I'm predicting, and I've got 3 flavors, mom, dad, and kid. Or I can think of it as like dad attitudes, mom attitudes, kid attitudes, and they're 3 separate things. So this sort of works both ways. The big difference is then whether or not you have a fixed intercept in your model that applies to every case or not. That sets up the rest of the interpretations. So in the first model here, I have 2 dummy codes in, dad is the implied reference. Same thing within R, I'm using GLS, so this is from the NLME package. It does all kinds of linear and nonlinear mixed models. This is the only way that I know of that allows us to tell it to allow the outcomes from the same family to be correlated and to have different variances and pairwise covariances. But the same thing here. I've got the general one, zooming in on my nice blue one here. That's how you know. If I have the 1, that's a global intercept that applies to everybody's row of data every time. So then everything else has to be some kind of deviation from that reference point. So this model is going to tell me what's the mean for dad, because that's when my 2 predictors would be 0. How does the mean for kid differ from the mean for dad? How does the mean for mom differ from the mean for dad? And to get the means for kid and the means for mom, I would add up the mean for dad plus the difference, and that can be done as a linear combination, as shown down here. So the same GLHT machinery we've been using to do linear combinations. If you see 2 1s in a series, that is adding those 2 fixed effects together to create a new term, and it's going to get a standard error and hypothesis test with it. Same deal here. If you see a -1, 1 pattern, that's a difference. So I'm asking whether the intercept differs between kids and moms in this case, as another piece of information. Here's then the output. This is the SAS version because it's more condensed, but I get the intercept that is for dad, the mean differences for mom and kid, and then I can get the other 3 fixed effects that I might want to know about. So that's the general intercept version. The other one is the no intercept, instead replace it with outcome-specific intercept versions. And so now I have this no constant here in Stata to tell me that, and dad is one of the predictors. So these are intercepts, 3 of them, 1 for each. Because if you think about how intercepts would be represented as a variable, like there's an implied 1 behind it that multiplies the variable, and if you see like the matrix version of this stuff, there's always a column of 1s. Well, that's what these are. These are columns of 1s, but there are also 0s in there for the rows that are not relevant. So functionally, it's like I've got 3 columns of 1s that turn on when it's that row for that type of person and off when it's not. So no constant is how you shut off the general intercept in these models. And in R, the same thing happens with a 0 instead of a 1. The first thing that made sense to me in R. I was like, oh, that makes complete sense that that's how you do it. I don't know what happens if you put in another number. I haven't played with that, but who knows. Then I had to fight with R to get answers that it actually computed, you know, par for the course. And so there's the equation and there's the results. Question or comment?
When we use the degree-specific intercept version, those intercepts are conditioned on the other outcomes being 0?
Yes. Yep, so it's set up so that there'd only be a 1 in one row at a time in this coding scheme.
Okay.
Yep, so I think of them as switches. Like it just turns on if it's for that row and it turns off if it's not. Yeah, that's what I say. Can I scroll up to show the C code for this model? This one? Yeah, so in this case, what we get directly are the 3 intercepts. I get 1 for each person. What I don't know, though, is if they differ from each other. Now, I may not care about that, right? If these are 3 separate outcomes, especially if they're 3 different scales, that's not a thing I would want to know. But in this case, I might want to know, hey, are dads more conservatives on average than moms? Are moms more conservative than kids? That kind of thing. And so those then need to be the linear combinations. So now I'm contrasting each pair one at a time to get the implied mean differences between my intercepts, which are just the means at this point because there's nothing else in the model. Okay, good? Okay, we're going to add some stuff. So, thing we did before, I asked if the adult child's gender significantly moderated attitudes. Turns out it only does for the kid. Stands to reason. So you might be saying, hey, that's a dumb thing to put in the model, but I had a reason. Because I wanted to show you that moving forward, the DV-specific intercept version makes it very obvious how you can only have a predictor for one outcome and not the others. You just don't put it in. So I have the effect of the adult child's gender only on the adult child. It's not in the model for the others because I don't need it. It wasn't significant and it isn't really meaningful in this case because I don't know what other children they have. Next question I wanted to ask is, does one person's own education predict the extent of their conservative attitudes? Expecting that folks who have less education might tend to be more conservative. That's my hypothesis. So I have a new term here. If I'm predicting dad, I'm predicting it with dad's education. Note the subscript of F, that's for family, because each family has one measure of their dad's education. These are intact families with one dad and one mom and one kid. So likewise, the kid's education predicts the kid's outcome, and then the mom's education predicts the mom's outcome. So you don't have to have the same predictors of each of your outcomes. You can leave them in or out in whatever ways make sense or are supported by your data. So in this version of the model, the effect of gender on the kid's outcome and then the 3 effects of education, these look like interaction terms, right? There's a hashtag in them and everything. And in R, we have the colon doing the same thing. These interaction terms. Yeah, one more, there we go. But these are not interactions. They are main effects specific to each outcome. So that's where it gets tricky because it looks like they're interactions, but in this way of thinking about it, they're not. Because the kid, for instance, is just a switch that says this goes to 1 if it's a kid row of data, it goes to 0 if not, in which case this drops out of the model. So you're building a separate model for each outcome simultaneously with whichever fixed effects you want to put in it. Otherwise, the rest of the code is the same. So if we look at the first tables here, this is the residual covariance matrix. So variance left over and covariance left over, correlations left over. Sometimes those are of interest as well. And then we have solution. So if we look at the pattern of these, all the effects of education are in the same direction. If to the extent that you have 1 more year of education, these are the changes in the extent of your conservative attitudes. They are lower, so less conservative. However, That only matters for dads. That's the only one that's significant. So dads who have higher education have less conservative attitudes, but there's no effect of one's own education for the adult child or the mom. So that might ask the question, well, does dad's education moderate the rest of the family? And yes, it's dad, because that was in the original like motivation for this example, that was their research question. And I was like, what about mom? Like, now, spoiler alert, mom's gonna matter, but not for like 20 pages or so. Hang in there. So I added, I left the own education predicting own outcome as a control and then said, what is the extra contribution of dad's education predicting the kid's outcome and the mom's outcome?
You could check the models then, couldn't you?
I can. So
No, I'm not saying that you have to, but you could because of.
I can't do model comparisons because I'm using an estimation method called residual maximum likelihood, in which case the fixed effects cannot be different in order to do likelihood ratio tests. But I can get like T's and F's and do combinations of slopes and slope differences as much as I want.
Okay, cool.
Yeah. Yeah, this is a distinction you'll hear more about if you take multi-level modeling stuff. That's the only place you'll see the word REML or hear about it. So same idea then in Stata, we're adding in dad's education as predictors of dad and kid and mom. Lots and lots of code. I know, it's a lot. Here's the story. So dad's education predicts his outcome still. Dad's education does not predict the kids or the moms.
Terribly.
Yeah, totally not. P-value of like almost 1. So I thought, like when I originally built this, that I was done. Like, there's my story. Doo-doo-doo. So I wrote a results section. Here it is. Look at all the words. Now, how do I know if this is sufficient? For the last like 6 weeks or so, we've been talking about distribution fit, right? Have I mentioned that at all? And this outcome is a mean across items that ranges from 1 to 4 with 2 boundaries, continuous in the middle.
Binomial?
Yeah, I could maybe binomial it. The problem is that the binomial family does not readily extend to multivariate or mixed effects models. Like I could not find like beta binomial for this. The other problem, and this is an aspect that is in the slides but I didn't mention today, is that the stacked data format of this forces the same parameters to be estimated regardless of which outcome. So for instance, if I had a stretchy factor, essentially the scaling factor for the beta binomial, it would force it to be the same for moms, dads, and kids, whether I wanted that or not. And the same thing happens in a negative binomial model, that stretchy factor is forced to be the same. If I had ordinal data, then all of the thresholds, the shifts between intercepts are constrained to be the same across outcomes. So you lose the ability to make it outcome specific in generalized models that are all stuck in one column. It's a software problem.
Yeah, I was just going to ask if that was software or theoretical.
It's a software problem, and that is probably the biggest reason to switch to path models is to avoid that problem. Because they are treated as separate columns, separate boxes in the pictures, and you can say this box needs this box needs that, and this box needs this other thing. And then you don't have to try and force it to be the same. Much more customized. But I think this outcome would be good to trick a binomial into it, except I can't really do that in the multivariate space. So I'm like, is this okay enough? Well, here's my evidence. Normality, it's not the best I've seen, it's not the worst. In terms of heterogeneity of variance, it looks like maybe less variance here than out here, but nothing like horrendous. I generated predicted outcomes, and they all stayed within boundaries. So I was like, you know what, it's fine. It's good enough at some point. However, I will show you something that you can do just in case to check involving robust standard errors. That is something we mentioned very briefly, the idea of heterogeneity corrected standard errors, or sandwich errors, they're called. It's really what it's called, right, Vladimir? The sandwich estimator, like that's the word, and there's like 4 kinds of them. So in M+, I'll show you how to do that as well. Okay, question, comment?
Yes, before you said that in our model, above, we were not using interactions. We had something like DV-specific slopes.
That is correct.
But then you said that you wanted to see if that education was moderating, which to me is a synonym of interaction.
Yes.
So the last three slopes there, are those,
These?
yes, exactly.
Okay.
Are those DV-specific slopes, or could those be considered interactions?
Great questions. I did not mean to say moderator. That came out wrong.
Okay.
That's the short answer. These are predictors. These are not interaction terms. This is the main effect of dad's education on dad outcome, the main effect of dad education on kid outcome, and on mom outcome.
Oh,
So these are main effect slopes, which you would just say the outcome is higher or lower.
Is that because they are kid, mom, or dad specific still?
Yes.
Okay.
Yes. So to get the implied interaction, which would be like, is dad's education a better predictor for dad than it is for mom? Which would be an interaction question. I did that as just differences down here. And so the only one that was significant was kid versus dad. The effect of dad's education matters more for dads than it does for kids. That's what that interpretation would mean. So those are analogous to moderation questions. Yes.
great. Lisa, for our intercepts in the model, you said that the intercepts will be conditioned on the other intercepts being 0, and we must add the predictors in the model. So what I mean is, for instance, the kid's intercept right now will be conditioned on the other intercepts being 0, but also in the predictors we have included in the model being 0.
Okay, yeah, let me clarify that. So it's not when these estimated intercepts are 0, it's when these variables are 0, which is only happens for the kid row. So then, yeah, like this is specifically for kids because that's when these two are 0. It is specifically for adult female children because that's the reference group, and specifically for kids who have a high school degree, who have a dad who has a high school degree.
Great.
Yeah.
Thank you.
Same principles, just higher level of complexity at the same time. Okay, so this is a little overwhelming. Can we agree on that? A little bit?
It's a lot.
It's a little bit, yeah. So the next half of this then is showing you the exact same model we left off at as a path model instead. But in order to be able to do that, I got to talk to you about what path models are.
Sorry, quick question. The model that we just did, was that the general intercept model or the specific intercept model?
The whole handout is specific intercepts after like the very first page of models.
Perfect, thank
Yep.
you.
Yeah, I didn't go back and forth because that just makes it even worse. It's,
Okay.
yeah, you got to not do everything at once. I've learned that the hard way. And I spoiled the story, right? I may as
Mentioned
well.
moms.
Yeah, it turns out moms matter. So what we're going to find is that our path model actually didn't fit very well. Now, this is a new definition of what fit means. Yet another one. Cough, cough, bridge question. The problem with the multivariate all-in-one column is that you don't have a global sense as to whether you're adequately representing the relationships among all of your variables at the same time. In univariate regression, like generalized and general models, we had predictors and one outcome. So we can know right away if this predictor is related to this outcome or not, because we've got a p-value and an effect size that tells us about that. But we don't have explicit information about how a predictor of that outcome might also be needed for this one too, and we didn't try that. So what's going to happen is these two paths right here, so from mother's education to child attitudes and from mother's education to father attitudes, that's not in our model yet. And we're going to find out the hard way that it's needed.
Could you have found out with the other model doing the same thing you did with dad?
Yeah, I could have tried it by basically adding in every possible prediction
yeah.
across the two and found that out, yes.
Okay.
But I had not done that.
I'm just checking my references.
Yep, that's one way that you could do it by staying in the univariate framework. Yep. So this is where we're headed. Other questions?